Here we are starting chapter 10 with our first section, graphing square root functions. And so this whole chapter is talking about square root functions and using square root functions, especially in geometry. So the first two sections are just talking about what they are and some specifics behind square root functions. And then the last two sections have to do with the Pythagorean theorem. So that's our map for this chapter. So for 10.1, our learning goals are I will graph square root functions, which is shocking, I'm sure, and also I will compare graphs of square root functions. So we'll be talking about the parent function and how it can be translated and how the translations are different. So starting off, we need to first remember what a square root function looks like. So our function f of x equals the square root of x. That's our most basic parent function here when we're talking about square root functions. And this, remember, is the inverse, or it undoes your x squared function. So the graph of the square root of x, if we think about making our t-chart, we can't use any negative numbers for x. So let's just identify all sorts of things. So we can't pick any negative numbers for x at all because we can't take the square root of a negative. That'll give us an imaginary number, which is something we're not discussing. So that means the first thing I can put in for x, or use as my input, is 0. If I put in 0, I get the square root of 0, which is 0. So 0, 0 is on my graph. Next, if I try 1, the square root of 1 is 1. So 1, 1 is on my graph. Now if I put in 2, I'm going to get out the square root of 2, which works out to be 1.4-ish. I don't want to worry about graphing that though. So the next thing I'm going to skip to is I'm going to put in 4 because 4 is my next square number. When I put in 4 for my input, the square root of 4 is 2. So 1, 2, 3, 4, 2 is on my graph. And if I wanted to, I could put in 9 and I'd get out 3 because the square root of 9 is 3. 6, 7, 8, 9. So that's going to be like up here. So you can see the general shape. And what we're getting here is basically it's half of a parabola. So this is what our basic graph is going to look like, our parent function. And then of course we can do transformations on that graph. So for example, well, before we do that, let's talk about the domain and the range just of this graph. You'll see that I can't put in any positive numbers for, or I'm sorry, any negative numbers for x. So my domain is going to be x is greater than or equal to 0. And then in order for this to be a function, my range then also has to be y is greater than or equal to 0. Because when I put in my positive numbers, I'm only getting out positive numbers. Now I know in the past we talked about how the square root of 9 is positive or negative 3. But you'll notice that if I graphed those, then I would have 2 points that have the same x value but different y values. And that's not a function. So in order for this to be a function, what we do is we restrict it. So we're only looking for the positive square root values. So that's kind of an important thing that we have to do in order to keep this a function. Okay, so like I was saying, we can take an equation, or take a function. Let's do y equals x, square root of x plus 2. And right away, you should have a pretty good idea what's going to happen to your original parent function, because this is your parent function, and then we're adding 2. And remember, in our previous examples, every time we added something off the end, that just shifted our graph up. Or if we subtracted something, that would shift our graph down. If we did something with the x, that would shift our graph left or right. So without even graphing anything, you should be able to look at this and recognize this is going to be a vertical translation of 2 units. It's going to shift our graph up 2 units. But of course, we can always pick a few points just to make sure. So if I put in 0, I get the square root of 0 plus 2. So that's going to give me 2. If I put in 1, I get the square root of 1, which is 1 plus 2 is 3. And again, I'm going to only pick perfect squares for under this root. So I would put in 4. Square root of 4 is 2 plus 2 is 4. So that should be enough points for me to get the general idea. When I put in 0, I get out 2. When I put in 1, I get out 3. When I put in 1, 2, 3, 4, I get out 3, 4. So there we go. You can see I have the beginning of my square root function. So let's look at how the domain changed, or see if the domain changed. The domain here is still only positive numbers. I can only put in positive numbers for x. So my domain is still x is greater than or equal to 0. So that didn't change. But if I look at my range, now instead of my y values being everything greater than or equal to 0, notice I don't have any y values here. So my y part of, my range has been shifted up 2 units, just like my graph was shifted up 2 units. So the range got shifted with that. So here's one example of graphing and talking about the domain and range. And then remember previously when we've done graphing, you've been asked compare it to the parent function, or compare it to the function of y equals square root of x. So in this case, we would say it's a vertical translation up 2 units. We can also have something that looks like this. So like I said before, this plus 5 is with the x. We also have a negative there. So that's going to change what's going on here. So if I asked you to find the domain of this function, remember that this, what's in this circle, has to be greater than or equal to 0. So in order to find the domain for this function, I just take what's under the square root and set it greater than or equal to 0. And then I solve. So if I solve this inequality, I would subtract 5 from each side. So that tells me that negative x has to be greater than or equal to 0. If I divide each side by negative 5, my fault. Negative x is greater than or equal to negative 5. Then I divide each side by negative 1. Remember, when you divide by a negative in an inequality, that flips your inequality over. So negative x divided by negative 1 is just x. Negative 5 divided by negative 1 is positive 5. So by solving this inequality, I found that my domain has been changed to x is less than or equal to 5. If I put in 5, I would have negative 5 plus 5 is 0. If I put in 6, I would have negative 6 plus 5, which is negative 1. That's not allowed. So I have to put in numbers that are less than or equal to 5 here. So my new domain is x is less than or equal to 5. And we could pick some points and graph them and see what this graph is going to look like, but you can do that on your own. I'm confident that you'll have the right idea. Okay, so the last example we're going to do by hand, y equals the negative square root of x minus 2. And I want you to graph, describe the domain and range, and also compare it to the parent function of y equals square root of x. What I'm going to do first is I'm actually going to figure out what the domain is. Because once I know the domain, then I know what points I can pick, and I can go from there. So remember, the domain comes from this, what's under the square root. So x minus 2 has to be greater than or equal to 0, which means x has to be greater than or equal to 2. So now I know to only pick numbers that are greater than or equal to 2. So if I make my chart, if I plug in 2, I get 2 minus 2, which is 0. Square root of 0 is 0. The negative square, or negative 0, and 0. If I plug in 3, 3 minus 2 is 1. The square root of that is 1. And then the opposite is negative 1. If I put in 4, that's not going to be, I'll get 2 under my root, so I don't like that. If I put in 6, though, I get 6 minus 2 is 4. The square root of 4 is 2, and the opposite is negative 2. So there are 3 points for my graph. So when I put in 2, I get out 0. When I put in 3, I get out negative 1. When I put in, that's 1, 2, 3, 4, 5, 6, I get out negative 2. So this is what, oops, I missed that point. Make it really big. This is what my graph is going to look like. So if we look back up here, we see it's been shifted over 2 to the right, which we should expect because of this subtracting 2. And then also it's been reflected, and that's because of this negative right here. So we have a reflection over the x-axis and a shift 2 units to the right. So that's how I would compare it to the parent function. So we've graphed it. We compared to the parent function. Now we need the domain and range still. The domain I figured out at the beginning. That was to help me pick my points. And now that I have the graph in front of me, I can see my range. Nothing I'm going to do is going to give me a positive value for y. Everything is down here less than or equal to 0. So that's how we are going to answer these questions. Okay, our last example we're going to use the graphing calculator for. The velocity y in meters per second of a tsunami can be modeled by the function y equals the square root of 9.8 times x, where x is the water depth, and that's in meters. At what depth does the velocity of the tsunami exceed 150 meters per second? So what we're looking at here, this is how fast the tsunami is going. This is how deep the water is. We want to know, when is it going 150 meters per second? So when does this square root of 9.8x equal 150? So what I can do to solve this is I'm going to do it a little bit differently than the book. Well, I'll show you how the book does it first. We put in the square root of 9.8x. Now if I hit graph on that, I can't really see a whole lot. Remember, x is representing the depth, y is representing the speed, and I want to know when it's 150, when the speed is 150. That's only 10, so I need to change my window, and let's go up to like 300. And let's also think about the depth. If I hit graph there, I can barely see my graph when because x is only 10. So let's put x out to, I don't know, 5,000, just to see what happens. If that's not big enough or if that's too big, we can always change it. Oh, that actually worked really well. Okay, so this is my graph. This is how the tsunami is changing speed as the water gets deeper and deeper. The tsunami goes faster and faster. So what I can do is, what what your book did, is they just pushed the trace button. And when you push trace, then we just follow right along our line, and we can see when x is 1,908, y is 136. So at about 2,000 feet deep, our tsunami is moving 140 meters per second. And I can just trace along until this is 150. You can see it's somewhere between 2,281 and 2,335. So maybe 2,330 is what I would guess. So we could say it's about 2,330. But we can also get this a little bit more exact. And what I'm going to do is I'm going to graph this guy in y1. I'm going to graph this one in y2. I want to know when these two things are equal. So if I graph both of them, they're equal when their lines intersect. And then I can do what I did previously, where I did second calculate, intersect, My first curve is the square root function. My second curve is just that linear 150. We're going to guess it's right about there. And then my calculator tells me it is actually x equals 2,295.9 meters. So at this depth, our tsunami is going 150 meters per second. So anything deeper than that, my tsunami will exceed that. So actually, my answer would be x has to be greater than 2,295. So that's how you can use your calculator to help you solve a problem like this. As for you, your homework for tonight, let's see, where can I find room? Your homework is on page 506, and you're going to do numbers 1, 2, 6 through 20 even. You're going to throw number 15 in there, and then 23 through 27, and 28 through 31. So there's your homework assignment for tonight. And hopefully between listening to me and flipping through your book and looking at the examples, you have a pretty good idea how to do this now. So good luck.